like, share, subscribe.
Hey y'all, welcome back. Number 85 says, in the xy plane, the graphs of which of the following functions are symmetric about the y-axis? Indicate all such functions. So we're looking for the functions that are symmetric about the y-axis. And so basically what that means is, let's say we have, it's just some random graph. To be symmetric about the y-axis, that means that whatever is on the left-hand side of the y-axis, let's say we have a graph that does something like this on the left-hand side, the right-hand side has to be exactly the same. So I'm going to just kind of freehand this. It won't be perfect, but you'll get the idea. Basically, the left-hand side needs to be a mirror image of the right-hand side. So, in other words, we have this line of symmetry that is the y-axis. And if we were to be able to fold our graph on the y-axis, every point on the left-hand side will match up with every point on the right. So, yeah, how do we determine that without actually having to do the graphs here? Because, with A, you might know what that quadratic looks like, but once we get to B or C, it becomes a little trickier to know exactly what the graph's going to look like without doing a bunch of work. So, here's the trick here, is we want to be able to determine that, so let's look at this graph that I've drawn here. Let's say, and I'm just making up these numbers, that this is at 1, and that at 1, this function value is, let's say, 3. Okay, just again, I'm just making up these numbers. But if that's the case, then if this is symmetric, then if x is -1, the y value should also be -3. Okay, so in other words, every x value, every positive x value's output should be equal to the negative value's output. Okay, in other words, another way to think about this is that f of x needs to be this, oh, how did all that disappear? What happened to my, okay, everything's going crazy here. Can I redo that? Okay, well, I'm not sure what just happened there. I'm going to have to just redraw this real quick. Cammy's going wild on me. Didn't like my graph. Okay, so just to kind of I'm going to just freehand this quickly. Let's say we've got something like this. So basically we're trying to get, that's not very good. I had it pretty good that first time. All right, so here we go. It's pretty ugly, but you get the idea. I don't want to waste too much time on that. But basically, here's the deal. If every x value, if every x value has the same output as its negative x counterpart, then it's going to be symmetric about the y-axis. And in this case, we call this an even function, if this is true. So basically, we are testing to see which one of these functions are even. And there's actually a little quick, a really easy way to tell without doing any algebra. So I'm going to tell you that shortcut up front, so we'll get our answer. But I also want to show you the algebra on how we can test this if we don't have a polynomial function. So when you have polynomials like this, the reason why this is actually called an even function is because each term that has an x has to have an even exponent in order for this to be true. Right? So right away I can say, oh, we've got an even exponent on this. We don't really care about the constants, although technically, you could think about this as like x to the 0, and 0 is even, so that does work. But you'll see algebraically here in a second why that's true. So we're expecting A to be even because all the exponents are even. B has an odd exponent, so that one is not going to work out. And then C, all the exponents here are even. 4 and 2 are both even. So this is going to be, so our answer is going to be A and C here. So if you're just looking for the answer, there you go. But if you want a little bit more algebraic justification for why that's true, let me go ahead and delete this graph here. We don't really need this. I just wanted to kind of give you an example of what an even function looks like, or one that's symmetric about the y-axis. But yeah, let's actually test each of these functions to see that they are in fact even. So if I'm going to do A here, I've got f of x equals x squared plus 2. And so what I'm interested in is to see, does f of x actually equal f of negative x? So to do that, we are going to substitute in negative x in for every single instance of x that we see. Now, if we simplify this and we get the original function back, that means that f of x is in fact equal to f of negative x. And that's what happens here with these even exponents. Anytime you raise a negative number to an even power, it becomes positive, right? Because a negative times a negative is positive. So negative x squared would be equivalent to just x squared. And so notice here that f of x is in fact the same as f of negative x. We get x squared plus 2. And this is only going to happen on these even exponents. You can kind of see why b is not going to work. I will show you here. But yeah, so the conclusion here is that f of x is equal to f of negative x. And if you can show this, then you know that it's going to be symmetric about the y-axis and by definition be considered an even function. So let's test out b here and show that this one's not going to be an even function. So for b, we've got f of x equals x cubed plus x squared minus 1. And it's really this x cubed that has an odd exponent that's really going to throw us off, because when we plug in a negative x and I raise that to the third power, negative x times itself 3 times is going to continue to be negative, because you can pair up 2 of those x's and a negative times a negative is positive, but if I multiply another negative x, it's going to end up being negative. So when I simplify this expression, I do get negative x cubed plus positive x squared minus 1. And so because f of x is not the same, and it has to be exactly the same, as negative f of negative x, we can say that, yeah, this is not going to be symmetrical. Yeah, let's change that to a not equals. There we go. Okay, so yeah, it's definitely not going to be B. And then, so let's just, for fun, test out C here, although we already know that's going to work because of all the exponents are even, but just to showcase this. Now, if you don't have a polynomial function on a question like this, like let's say you have like an e to the x or natural log or a rational function or something, you know, something a little different, then you can't just look at the exponents in that case, and you will have to do this algebra where you're plugging in negative x in place of x and seeing if you end up with the same function. So that's really the only reason I wanted to go through this algebra with you, is so you can see kind of what you're looking for when you don't have a polynomial function. Now all of these are polynomials, so we can kind of shortcut our way through it and just look at the exponents. But yeah, so anyway, if I plug in negative x here, we can see both of these x's have an even exponent. So that means that when I simplify that, you know, when I multiply a negative number times itself an even number of times, it's going to end up being positive. So this will end up being positive x to the fourth, positive x squared, and you can see that we ended up with the exact same expression for f of negative x that we had for f of x. And so we can conclude here that f of x equals f of negative x. So yeah, this was one of those multiple choice where you have multiple possible answers. So our answer is going to be A and C. And that's about it for number 85. Thanks for watching, and y'all have a great day.